Hello, this video is entitled Arc Length and Curvature. Now you might have seen them back in Cal 2, and if you didn't, that's okay, but arc length in parametric form of a plane curve. So they don't bother to cover that here since it's already been covered earlier. We're just going to look at only a space curve. But the formula is very similar, so if you saw this in Cal 2, you just wouldn't have seen the z component here. So we're going from a to b of the square root of x prime of t squared plus y prime of t squared plus z prime of t squared. And that also happens to be that formula is the magnitude of r prime. Same thing. But when you expand it out, which is what we need to do anyway, it's going to look like this. So it's pretty straightforward. It's just a matter of the integration necessary. Anything under a square root has the potential to get rude, but any questions that I would ask on an exam or quiz, or in other words, just because it's square root, I don't think you have to worry about trig substitution or anything like that. With that being said, let's look and see what we have here. So we're going to find the arc length of this vector valued function, which I went ahead and just converted it from standard unit vector form to component form. So I would just be 1i, so it's 1 t squared t cubed. So I need the magnitude of this, which is 0, and 2t's, the derivative of t squared, of course, and then t cubed would lead to 3t squared. And the magnitude then would be 0 plus 2t all squared is 4t squared, 3t squared, 9t to the fourth. Now, I guess if you're able to use technology to do this, that's fine. But if you're in a situation where you have to work the problem out for your instructor, then I want you to see how this is done. But technically, if you're using just the regular graphing calculator technology, you can integrate this. Of course, you don't have to use variable t either. You can just use x, but you can do the f and int on this right here. So the trick on this one is factoring out, because it looks kind of, how am I going to integrate that? That looks weird. But you have to factor out a square root of t squared, which is the absolute value of t. T will be positive here. So now when this t comes out, you're left with the square root of 4 plus 9t squared. Now you've turned it into u substitution. So that's why it looked weird. But as soon as I did that, it's now just straight u substitution that you would have learned in Cal 1. So I'll let u equal 4 plus 9t squared, du equals 18t dt. So 1 over 18 du equals t dt. And then I change my limits of integration. So if I put 2 in here, I'll get 40. I put 0 in here, I'll get 4. And so let's see what we have here. So then it just turns into, so we got the 1 over 18 we have to move out of here. And then now you're just integrating u to the 1/2 from 4 to 40. So it's pretty straightforward at that point. It'd be 1 over 18 times antiderivative of this would be 2/3 u to the 3/2. So 1 over 18 times 2 over 3 is 1 over 27. So it's 40 to the 3/2 minus 4 to the 3/2. And that's technically correct, but I decided to get a little cute with the answer here. Probably because I wanted to get closer to what the maple answer looked like. But I factored out a 4 to the 3/2, which 4 to the 3/2 is 8, because it's the square root of 4 cubed. And then 10 to the 3/2 is 10 square root of 10. But really, where I have that flag, even if you're looking for an exact answer, that's correct. That's an exact answer. And like your instructor says, I don't want decimal, I want exact answer. This is just a different way to rearrange it. But anyway, if you take 8 over 27 and you multiply it through these parentheses, you'll get this answer that Maple came up with right there. Of course, the calculator is going to give you a decimal answer. roughly 9.0736. So that's the, I'll let graph the curve. So that's roughly a length of 9 right there from 0 to 2. All right. Let's take a look at the next example. For this example, R of t will be 6t, 4 sine t, 4 cos t. And we're going to find the arc length on the path from 0 to 2 pi, which here's the graph of it down here. It would have kept spiraling had we kept going on and on. Would have kept spiraling around. So r prime of t is 6. Derivative of 4 sine of t is 4 cos t. Then derivative of 4 cos of t would be negative 4 sine of t. So we have to find the magnitude of that vector. So it's going to be 6 squared is 36. We have 16 cos squared t. And you square the last component, is 16 sine squared of t. Now this integral turns out to be very, very easy, but it could be very, very frustrating if you don't at first realize what's happening here, because if you're trying to use some other method to do this, you would really mess this up. But this is really important that we recognize, because cos squared t plus sine squared t equals 1, that means 16 cos squared t plus 16 sine squared of t would just equal 16. So look at that, all the variables are gone. So we just have 36 plus 16. So it's the square root of 52 dt, and the antiderivative dt would be t. So it's the square root of 52 t, 2 pi minus 0. So that's the correct answer, and I went ahead and just reduced the square root of 52 just for the heck of it. It's 2 square root of 13, so that makes it 4 pi square root of 13. But it's nothing really wrong with this answer right here either. So this, then it just got a decimal answer just to show you. So evidently that thing stretches out at 45.3 units roughly. All right, so let's take a look at the next one. So this arc length's not too bad. It's real straightforward, plug and chug. Just have to get the integration correct. Concept's easy enough. So here's our vector valued function. We're going from 1 to 3. So here's r prime of t. The derivative will be 2, 3. 3 halves times 8 is 12. That would make that t to the 1 half. So the magnitude, 2 squared is 4. 3 squared is 9. 12t to the 1 half squared is 144t. So that means we're integrating 13 plus 144t to the 1 half from 1 to 3 to get our arc length. And this is pretty much straightforward u substitution. So if you let u equal 13 plus 144t, that means du will be 144 dt. And then 1 over 44 du would equal dt. And then I'll change my limits of integration. So I put 3 in here. I'll get 445. I put 1 in here. I get 157. So I have a 1 over 44 out here. Antiderivative of u to the 1 half will be 2/3 u to the 3 halves. So to combine those two fractions, you get 1 over 216. And then basically you have 445 to the 3 halves minus 157 to the 3 halves. Those aren't going to really simplify much, but what you're likely to see, though, when you're looking at answer choices or whatever the case may be, is it probably would rewrite that as 445 times the square root of 445 minus 157 times the square root of 57. That doesn't make the answer any more correct. It's just a different looking version of the same answer. Now let's take a look at something called curvature here. Curvature is a measure of how sharply a curve bends at a point. Now that could be important in various applications. Let's say maybe you design, you're going to be an civil engineer or something or whatever, and be part of designing race car tracks or something like that, where Obviously, too much curvature would probably cause too many wrecks, and not enough curvature is probably a little on the boring side, but for racing. But anyway, so that's it's hard to really get much of a feel. Like, for example, if someone tells you the curvature is 5, that doesn't really tell you all that much, unless you're maybe working with curvature a lot and looking at the pictures. But in this case, numerically it doesn't matter, but I'm just kind of showing you in this graph that you see how this curve bends more at that point than that one does. So regardless of what the numerical value is going to be, it's for sure going to be a larger curvature value for this one on the left because it's a sharper bend. Now you look at these formulas, you might find it surprising the statement that I make down here. But you're going to have to trust me on this one, and you can use that first one if you want to. But there's two ways to get this. It's the magnitude of t prime of t divided by the magnitude of r prime of t. Or you take r prime of t, cross product it with r double prime of t, and get that magnitude over r prime of t cubed. I promise you that is much easier, because that t prime of t is messy. But whatever makes you happy. I'm telling you, this formula will make you happy. So here's a RT is TI plus T squared J. And I kind of waited too long. I should have put the zeros in there earlier here. But anyway, yes. So you see there's no K there. So we have to use the cross product formula, we have to put zeros in there, which is allowed. Obviously a cross product only works for vectors in space, and it's okay to add zeros at the end of that. But anyway, here's the first derivative, 1 comma 2t. So you put 1 in there, it's going to be 1 comma 2t. And then take the next derivative, will be 0 and 2. And then the derivative 1, put in r. Oh, that's what's wrong here. This needs to be fixed. I knew something didn't look right here. I'm going to fix it right now. That should say r double prime. There we go. R double prime of 1 then would be 0, 2. Because there's nothing to plug in anyway, so it's just going to be 0, 2. Okay, and then like I said, here's what happens when you convert them to space vectors to use this formula. You have to add the zeros to it. So we convert them to space vectors and do a cross product using the cross product formula. And here's another mistake that I see. That should be a 1 right there, not a 2. So let's fix that. And I'll just keep talking here, but we do a cross product, and it's going to be 2 for the cross product. And let's see. And of course, the magnitude of a vector 0, 0, 2, the magnitude of that will be 2. All right, now then we need the magnitude of just r prime of 1, which is right here, 1, 2, 0. That magnitude will be square root of 5. So our answer will be 2 divided by square root of 5 cubed. And whether or not you have to rationalize that is up to the instructor. I did this problem in Maple, and this is the same answer, because if you split this up, that would be 5 square root of 5. Then if you multiply top and bottom by the square root of 5, it would equal that answer right there. So, all right, curvature, not too bad. Now, if you use that cross product formula, now I'm not going to go through all the details of this one, but I'll just kind of leave it here if someone that's not in my class, doesn't have the access to my notes. So I'll leave it there if somebody wanted to look at it. can pause it. But anyway, I'm using that formula right here, the t prime of t magnitude divided by r prime of t magnitude. A lot messier. But long story short, I end up with the same answer. That is the same answer as the one on the other page. So hopefully that will be a convincing reason then not to use that formula when you can just use the cross product formula. So here's the next example. Our vector value functions 4 cos t, 3 sin t, and t. And then we have a point, -4, 0, pi. So this is one where you give the point, given the point, you have to find the t. But this one's super simple since it has a t component right there, and that t component is pi right there. Then that means t would have to equal pi. So that one worked out pretty well. Let's take the derivative. 4 cos would be -4 sine of t. 3 sine would be 3 cos. T derivative would be 1. So r prime at pi would be 0, -3, 1. The second derivative would be -4 cos t, -3 sine t, and then 0. And you put pi in there, you're going to get 4, 0, 0. And if you do a cross product, r prime of pi, with crossing it with r double prime of pi, you're going to get 0, 4, 12. And the magnitude of r prime of pi, which we need for the denominator of our formula, is 0, -3, 1. So the magnitude would be the square root of 10. And I just happen to pull out a common 4 here. We've done that whenever with magnitudes before. It's not wrong if you don't, but I pulled the 4 out and then took the magnitude of 0, 1, and 3, which happens to also be the square root of 10. So you have 4 times the square root of 10 divided by the square root of 10 cubed, which to me, that's a perfectly acceptable answer. But it does simplify to 2/5 because one of the square root of 10s would cancel with the square root of 10 on top. And then you would have 2 square root of 10s on the bottom multiplied together would make 10. So 4/10 would then reduce to 2/5. And here is that graph. There's the curvature values, 2/5. Here's where the point is on that graph, and a little bit of a bend there. Like I said earlier in the video, it's not necessarily easy to know what you are to quantify. Oh, that curvature looks like it would be a 3. It doesn't really. It's hard to really know that unless you were to work with curvatures and were used to seeing them a lot. But point being is that it's not bending very much, you can see. So the fact that it's a small curvature makes sense. I guess the point I'm trying to make is, if I go over to this point right there, you can see there's more bend there. So whatever, that one would have produced a larger curvature than 2/5. But I don't have the skill to look at that and know, what I think it would be, or I couldn't. Any estimate would just be made up. But the fact that it bends more than this other one is definitely greater than 2/5. That much I can say for sure. Okay, let's take a look at this curvature. 3t squared, 2t, 3t. R prime would then be 6t, 2, 3. Now notice this one's not asking at a particular value of t. So we're just finding the general form of the curvature as a function of t. And then the next derivative would be 6, 0, 0. So when you do the cross product, you actually don't have any t's in this one, but it is possible there could have been t's in that cross product, but you won't in this example because you're going to be multiplying 6t times 0. So it wipes out any possible t you could have gotten. Well, actually twice. You're going to have 0 times 6t. And the cross product would give me 0, 18, -12, which I factored out of 6. So it's 0 squared plus 3 squared plus -2 squared, which makes 6 root 13. And then the magnitude of r prime, now that will have a t. So it's 6t squared makes 30t squared total, plus 2 squared plus 3 squared would give me 13. So we have 6 square root of 13 divided by the square root of 36t squared plus 13 cubed. I just rewrote that as a 3/2 power. It doesn't make it any more correct. So this is evaluated as a function of t. Now, if you're evaluating this at a specific value for t, I would just put in, like we've been doing, put the value in for t early and take care of it. But the one advantage that this particular method would have is if, let's say, maybe you were asked to find, not by me, but if you were asked to find, okay, let's find the curvature at 4 values. Let's say t equals 1, 2, 3, and 4. This would be more efficient because when you have this formula in terms of t, all you would have to do is just replace that t in the denominator with 1, 2, 3, and 4 separately, and it would get you those 4 curvatures. Versus doing it the other way, you would have to do, r prime of 1, r double prime of 1, r prime of 2, r double prime of 2. You'd have to work it out this way 4 times. But so that would be an advantage for doing multiple curvatures. But for one curvature at a numerical value, you would just use that numerical value. Here's curvature in rectangular coordinates. Let's take a look at this. This formula, so this is y as a function of x instead of parametric form. So the curvature is the absolute value of y double prime, because the value of y double prime could be negative and curvature is a positive value. So we need the absolute value there just in case. The curvature formulas that we're using above, they involve magnitudes. So that takes care of any issue with any negatives or whatever. So anyway, so it's the absolute value of y double prime over 1 plus y prime squared, all raised to the 3/2. So we'll just look at one quick example of this. So y equals 2x plus 4 over x, which obviously is the same thing as 4x to the negative 1 at x equals 1. So I'll take the first derivative, which will be 2, and if that's 4x to the negative 1, this will give you negative 4x to the negative 2. Put in 1, we'll get 2 minus 4 is negative 2. And then the next derivative would be negative 2 times negative 4 is 8. Subtract 1 makes that negative 3. Put in 1, we get 8. So we use this curvature formula. Well, y double prime of 1 just happens to be positive. But if it hadn't have been, we'd have made it positive, because the absolute value of 8 would still be 8 divided by 1 plus this negative 2 right here squared, all that to the 3/2. So it's 8 divided by 5 to the 3/2. And once again, I would not care about trying to rationalize any denominators. You would only do that as if it was required by the instructor. Well, anyway, that will conclude this video on arc length and curvature.